So this is you've done equations of lines before, and today we're going to do the vector equation of line. So equation of a line that you know is y equals mx plus b. And that works for two dimensions. Your m is your slope, your y is your y-intercept. So if you had a y-intercept of 1 and a slope of 2, you'd go up 2 over 1, and you'd have that equation, y equals 2x plus 1. But that only works for two dimensions. What we're going to look at is how we can use vectors to make an equation of a line so that we can have an equation of a line in 2 dimensions and in 3 dimensions as well. And the idea is this. So here's our line. We've got some line, whether it's in 2 dimensions or 3 dimensions, that's blue like this. The direction of that line is the vector a to c. Does that make sense? That's the direction of that line. What we're going to use is we're going to use our position vectors. So here's our origin. And so we've got a position vector a and a position vector c. So we could say that our direction vector a to c is just minus a plus c. And that's what we've done so far. We've done that when looking at position vectors already. Now, any point that's on the line can be represented by this point r. And this point r can slide along that line. So the way that we make an equation of a line with a vector form is we say start with a point that you know is on the line. And usually that's either a or c. So I'm going to start with the point A. Then any point, any black point along this blue line will just be a certain distance in the direction of AC. So for example, if we started at A and said, let's go a distance of 2 in the direction of AC, it would get us maybe to point R. If we made that distance further, it might get us here. If we make that distance negative, it will go backwards along that line. So our equation of our line we write as any vector r so this r is any position vector on the line. So any position vector on the line has vector a, and we can sort of think of that as a starting point. And that starting point can be anywhere on the line. Vector c minus a well, that's just vector AC, negative a plus c, which we said up there before. And then finally, we have a parameter t here, which says, basically tells you how far to go in that direction. And since t can be any number, you will get all the position vectors, and in the end, would make that equation of that line. So to recap, we've got a point on the line. We know the direction of the line. And then depending on what the t value is, we can create any point on that line that we want. And so all those points put together becomes our equation of our line. So often we make this equation just simplified like this. any vector, any starting point, and then b is our direction vector, which you just get from having 2 points on the line. So unlike y equals mx plus b, y equals mx plus b has a slope, the m, that's very much like your direction vector b, because your slope tells you how far to go and what direction your line's going. So slope and direction vector are basically the same thing. But in y equals mx plus b, the b is a specific point. It's always the y-intercept. With the vector equation of the line, the vector a can be any point on the line. So there's a little bit more freedom there with the vector equation of the line rather than y equals mx plus b, because you can use any point as your starting point. So if we were in 2 dimensions, your vector would be x and y, would be its elements, and then you would have your direction vector and your starting point. And if you looked at each individual coordinate, we call it the parametric form of the equation. So just looking at the x coordinates would just be x equals a1 plus t times b1, and the y coordinate would be similar. Now, if you rearrange each of those equations to get the t value by itself, then you would get one equation with x and one equation with y. And since you have 2 equations and they're both equal to t, you could equate them, and then you would get the Cartesian form. And we're going to see with the Cartesian form, you're going to be able to rearrange that to look just like y equals mx plus b. So any equation of a line will have a starting point and then a direction vector. Well, we're told it passes through the point 2, 5, so we can write that as a vector, a position vector 2, 5. And since it's parallel to 3, negative 4, that's our direction. So this is our vector equation of a line. If we were going to write the parametric form, your x coordinate is 2 plus 3 times t, and your y coordinate is 5 minus 4t. For the Cartesian form, can you see that you could rearrange this one so that t is equal to x minus 2 divided by 3? And this one you could rearrange to get t by itself to get y minus 5 divided by negative 4. So the Cartesian form of the line is just x minus 2 divided by 3 is equal to y minus 5 divided by negative 4. Now, just to play around with this so that you can see how the math that you've done in the past is connected to the math that we're doing right now. You don't have to write this down. But if you wanted to find y equals mx plus b, in this case, we're told that it goes through the point 2, 5, and it's parallel to the vector 3i minus 4j. Well, what does 3i minus 4j mean? It means you'll go 3 to the right, down 4. That's the vector that it's parallel to. Well, that tells us a slope. that tells us we know that our slope, rise over run, we're going down 4 over 3. It would have a negative slope, and your slope would be negative 4/3. So as far as your equation of a line goes, you know that the slope is negative 4/3. In order to find b, well, you've got a point. You can plug that point in. So when y is 5, x is 2, this would be 15 over 3 plus 8 over 3. B would equal 23 over 3. So y is equal to negative 4/3 x plus 23 over 3. That's your equation of a line. A couple of things about our equation of a line. It has fractions right now. It's not really nice to look at. As far as graphing it, it wouldn't be that much fun to graph because the point itself, if you started with your y-intercept, is a fraction. And then to go down 4 over 3 from that fraction, you'd end with another fraction. Probably it would be nicer if you were graphing it to start with this point, 2, 5, and then use your slope going down 4 over 3 to find another nice point, and you could graph that. So here's our equation of line, y equals mx plus b. If we wanted to get that equation of a line from what we did with vectors, our Cartesian form could do that. What I'm going to do right now with this Cartesian form, just going to create some space up here. If you would multiply both sides by negative 4 and 3, basically to cross multiply, you get negative 4x plus 8 equals 3y minus 15. If you would get the y by itself by adding 15 to both sides, you get negative 4x plus 23 equals 3y. And now if you divide it by 3 to get y by itself, you get negative 4 over 3x plus 23 over 3, which is exactly the same as y equals mx plus b. Now this works great for 2 dimensions, but what we can do with the vector equation of line is we can also do it with 3 dimensions. The other nice thing about the vector equation of a line is you're not dealing with fractions. You're just dealing with one nice point and the direction that you're going in. And so a lot of the math is easier to work with because you're dealing with nicer points. So again here, we want to write our vector equation of a line. We have a starting point. It goes through 2, 5. What's our direction vector going to be? Because it's perpendicular. This vector is 3, 1. Do you remember how to do our perpendicular vectors? Right, the perpendicular vector is the dot product. So if you did the dot product with this, it would equal 0. The numbers would have to be mixed so that they would 3 times 1 and 1 times 3. And then one of these has to be negative. So it doesn't matter which one you make negative, but that will give a different direction vector. That will make sure that the dot product is 0 and that it's perpendicular. So our parametric if we just look at the x coordinate and if we look at the y coordinate, and for our Cartesian, do a little bit of mental math. Can you solve for t in your mind for both of them? Whew. because I get t by itself by subtracting 2 here, so I'll get x minus 2. If I get t by itself here, I'd have to subtract 5 and then divide by negative 3. And then that makes our Cartesian form. In the Cartesian form, if you cross multiply and then solve for y, you'll get x plus b. Oh yeah, I want you to try this one on your own. So if we were to draw out a picture of what's happening here, we've got the point A, which is 1, 4. And the point B, which is 5, 8. And our line goes through both of those. So we have a position vector A and a position vector B. That kind of idea. And what we're looking for in our equation of our line is the equation for any point along here, any vector, position vector r, that happens to be on that line. So putting that together, for vector A, you could either use A that we've written here, 1, 4, or vector B. It doesn't matter which point you use as a starting point. They will both work. So if you use 1, 4 or 5, 8 there, it'll be fine. But in this question, we have to do some calculations because our direction vector is this. That direction vector right there. How do I start at point A and go to point B? So my direction vector will be the same thing as my vector AB. Well, in order to go from A to B, I could go negative along A to get back to the origin, and then add B, which is basically the same as B minus A. And if you did B minus A, that's 5, 8, minus 1, 4, our direction vector is going to be 4, 4. Now for your direction vector, if you wrote 4, 4, it's perfectly fine. If you wrote negative 4, 4, because you did, maybe you did A minus B, but then you would get negative 4, sorry. That would be fine as well. This direction vector says go over 4 and then go up 4. That's basically like a slope, right? If I went over 4 and then up 4, that's how I get to that point. What would you do if you had that slope? If you had that slope and it was 4 over 4, you'd probably reduce it to 1 over 1. So if you wrote your direction vector here, instead of 4 over 4, if you wrote it as 1 over 1, that would be correct as well. So there's a fair number of options of things that you can do here. And all would be correct. We have this. We could write our parametric using the values that I have here. This would be 1 plus 4t, and y would be 4 plus 4t. And for your Cartesian, solving for t, you'd get x minus 1 over 4, and that would be equal to y minus 4 over 4. So now let's go to 3 dimensions. It's exact same idea. You need to have two position vectors. So just like before, we've got some position vector P that goes from O to P, some position vector Q that goes from O to Q, and here's our line that passes through those points P and Q. So writing our equation of our line, we need a point to start, and you could choose P or Q. I have a habit of always choosing the first point. Then our direction vector from P to Q will just be negative P plus Q. If you did that, negative P, 1, 5, 3, plus Q, 2, 0, negative 4, you would get 1, negative 5, negative 7. And that would be your direction vector. Make that a little smaller. So here was our equation, and we're asking, does this point, negative 1, 3, 5, lie on that line? How did you do that when it was y equals mx plus b? Like if I wrote the equation of a line here, y equals 3x plus 5, and I asked you, is 2, 10 on that line or not? You'd plug them in, right? If you plug in 2 for x, does it equal 10? In this case, the answer is no. And since it doesn't equal 10, 2, 10 isn't on the line. In fact, 2, 11. 2, 11 is, but 2, 10 isn't. So you check to see if that point works. We're going to do the same thing here. We're going to check to see if the point negative 1, 3, 5 is on that line. And to check it, often it's going to be the easiest to use the parametric form of the equation. So when x is negative 1, here it's saying that we would have 1 plus t. When when y is 3, we should have 5 minus 5t. And when z is 5, we should have 3 minus 7t. Now, if that point is on that line, then there exists some value t that makes it work. So if I look at my first equation, can you see that this would work if t is equal to negative 2? So now the only way it's possible is if t is equal to negative 2. What about the second equation, though? Right? If you plug in negative 2 for t, we get 15 here. It doesn't equal 3. So right from here, we know that t equals negative 2 does not work. We can already say that we'll know that this point is not on the line. In fact, if we solve for t in this case, we get t is equal to 2/5, not equal to negative 2. And if you look at the last one, t is equal to negative 2/7. So in order for that point to be on the line, it needs to get the same t value for all three. So here's another point. Check this one. All right, so here are our parametric equations. Well, I'll just put the point in right away. So we're checking when x is 3, it should equal this. 5 and 5. So here we get t is equal to 2. And the second one, t is equal to 2. And then the third one, t is still equal to 2 over negative 7. So just like the last point, the answer is no. After you did the first two, did you think for sure the third one would be t equals 2? Isn't that what teachers normally do? The first example doesn't work, so then they're nice and show you an example that works. Well, I'm not that nice kind of teacher. So sometimes we get like different variations of the same thing. So you have to be able to work with parametric, the Cartesian. This one's given it as the vector equation of a line is given just as one vector. Can you rearrange this to look like this form? What's the point that's on the line? Because we need something plus t times something. Well, could you write this just as the parametric form? The parametric form, well, your x coordinate is 3 plus 2t. Your y coordinate is 5 minus 5t. Now, if that was your parametric form, what would have been in your original vector form? Okay. Perfect. So it's just playing around with it and rearranging things. Part B, a little bit of review. Do you remember how to find the unit vector? We need to find a unit vector in the same direction as that line. What direction was that line going in? 3, 5 or 2, negative 5? 2, negative 5. So this is our direction vector. So now we know that this is the direction that it's going in. How do we find our unit vector? So if this is our vector u, what is our unit vector for that? Well, the unit vector is a length of 1. How long is this vector? What is the length of vector u? Remember, we do a squared plus b squared. So that vector has a length of root 29. So our unit vector will be 1 over root 29 to make it equal to 1 of 2 and negative 5. In part C, we want to find the Cartesian form, so just have a look, 3, 5, 2, negative 5. So there was our vector equation of the line. If we want the Cartesian form, you'd probably have to start by going to the vector form. And once you have the vector form, then you can rearrange those to get your Cartesian form. So this next question also has our vector equations in a weird form. So let's see if we can rewrite the line L as a vector plus t times a vector, and rewrite our vector, our line M, as some vector plus, the one has S, the one has T. So the parameter doesn't necessarily have to be the same. Some questions they will be the same. You can choose any variable you want for this. So the question is, can you figure out these from this form? What do the I, the j, and the k represent? The I represents your x coordinate, right? So if we look at that, we know that our x coordinate is 5 minus 4s. Our y coordinate is 3 plus s, and our z coordinate is just 2s. If we had those parametric equations, could you go back and see what would be in your original equation? What would be a point on our original equation? 5, 3, and 0. And then s is getting multiplied by -4, 1, and 2. And in our second equation, we have an x coordinate of -3 minus 4t, a y coordinate of 7 minus t, and our z coordinate is just 6. So a point that it passes through would be -3, 7, and 6. And t is getting multiplied by -4, -1, and 0. This is where this, if I had a three-dimensional space, it would be really nice because I could draw out one of these vectors. I could just pick the point and draw a three-dimensional vector and draw the other three-dimensional vector, and you'd see in this three-dimensional space that these two three-dimensional vectors cross at some point P. Now, our job right now is to find that point P. Now, if they cross at the point P, they're going to have the same x coordinate at that point P, the same y coordinate at that point P, and the same z coordinate at that point P. Now, again, this is where we're going to use our parametric equations. We've got parametric equations for our x coordinates, parametric equations for our y coordinates, and parametric equations for our z coordinates. So that means that if the x coordinates are the same, then 5 minus 4s has to equal -3 minus 4t. And if we just looked at the x coordinate, there's no way that we can solve this, because we have two things we don't know, s and t, and we only have one equation. If we write out our y coordinates, we'd have 3 plus s needs to equal 7 minus t. And just using that one equation, 3 plus x equals 7 minus t, we couldn't solve that either. But both of those equations together gives us two equations with two unknowns. And so that means we could solve that with systems of equations, or maybe we want to set up matrices and solve it using our matrix techniques, or use substitution or elimination. We have tons of techniques to solve this already. But I'm going to say be careful, because even though you might be really excited to solve for s and t already, it's worthwhile to equate all three equations, because when we equate our z coordinates here, our z coordinate is really nice because it makes an equation with only one unknown. So from this one, you can find out right away that s is equal to 3. If s is equal to 3, you can choose either the first or the second equation and say, well, if s is equal to 3 and you plug it in, then t has to equal 1. So you plug in s equals 3 and solve that equation for t. Can you see that t would equal 1? We need to check to make sure the last one actually works. When s is equal to 3, does t equal 1? Well, when I plug in s equals 3 into this side here, I'm going to get negative 7. And when I plug in t into this side, I get negative 7. So when I check it, yes, it does work. So we know that s is equal to 3 and t is equal to 1. Now you can go back to any of your equations, either your vector equation for L or your vector equation for t, and you can plug in 3 for s and see what you get, or you can plug in 1 for t and see what you get. Either way, when plugging that in, you get negative 7, 6, 6. And so that is the point that's in common between the two of them. I plugged in 1, so negative 3, basically, if you want, you can use your parametric equations. Plug in 1 for t, what's your x coordinate going to be? Negative 7. Plug in 1, what's your y coordinate going to be? 6. Plug in 1, well, there's nothing to do there. It stays 6. Or you could have gone to your parametric equations here. Plug in 3 for s. What's their z coordinate going to be? It's going to be 6. What's your s? 3 for s, you're going to get 6. 3 for x, you're going to get negative 7. So once you've verified that s and t work for both of them, because again, sometimes you'll solve for s and t and it will work for 2 equations, but it won't work for that third one. So these two vectors in 3 dimensions crossed at the point P. What is the angle between them? Well, to find the angle between them, we had this formula. Cos theta is equal to the dot product of whichever vectors you're using. Since we have lines P and Q, it'll be the dot product of P and Q, and the length of P times the length of Q on the bottom. The question is, what vectors are we going to use for P and Q? We've got our vectors of equations of the line here. We found the point where they intersect. But right now, for choosing P and Q, we have 5 column vectors here. We have their point of intersection, we have in line L 2 vectors, and we have in line M 2 vectors. So if you were going to randomly choose 2 of them to use, 5 choose 2 is 10, you'd have a 1 in 10 chance of picking the right 2. Probably not a good decision just to randomly pick 2 vectors. Okay? So which 2 vectors are we going to find? Which 2 are we going to use? Because we've got our line, let's say this is line L and this is line M. I'm not sure if that's matches with the letters that we used or not. And I need to find this angle between L and between M. How do I do that? Well, if I used the point where they intersect, somewhere over here is the origin, right? This point where they intersect was this vector. Is that a vector that we want to find the equation between? No. That's just a position vector of what we started with. When we look at our equation of a line, remember our equation of a line, these are always starting points. They're points on the lines, but they're starting points. So if I look at one of the starting points on the green line and one of the starting points on the blue line, well, those would just be position vectors like that as well. But what we're looking for is we're looking for this and this. Those red vectors are the direction the line is going in. Does that make sense? So when we want to find the angle between 2 lines, we need to use the direction vectors. What are those vectors, those red ones? Well, if we go back to our equation, these were our direction vectors. So we need to use the direction vectors. I'll say P is my direction vector for my first one. Q is my direction vector for my second one. P was negative 4, 1, 2. And Q, negative 4, negative 1, 0. So now we can plug things in the dot product, multiply your corresponding coordinates, so 16, negative 1, and 0, and add them. What is the length of P? Square each one, 16 plus 1 plus 4. That'll be the square root of 21. Square each one for Q. 16 plus 1 is the square root of 17. So we have cos of theta is 15 over the square root of 21 times the square root of 17. Cos inverse and you get theta equals 37.45 degrees. Couple of things. Since cos was positive right here, since the dot product was positive, we knew that we were going to get an angle that was between 0 and 90 degrees. That was one of the things that we noticed from the dot product. The key thing, whenever, quite typical question to find the angle between 2 lines, you have to use the direction vectors, because those are the red ones. The starting point is just a position vector. Again, obviously, you're probably a good guess to guess not to use the point of intersection. But you need to use any two direction vectors. And then they get put together, and then you can find the angle between them. I will hand out section 13D for you, and we'll work on that for the rest of the class.